Welcome everyone. So this is our 78th live stream geometry. We have 3 people here with us so far. And today I'm taking problems that were, most of which were posted on Art of Problem Solving by the user RopuToran. So I got his or her permission. I don't know if it's a boy or girl, but I got their permission to use the problems. He or she said that they some of the problems they created themselves, but most of them they got from other sources, but I couldn't always find the other source. So if you want to join us in a future session, feel free to email me at mgreenb801@gmail.com. It's going to be in the description of my video, and we meet every Sunday at 8 a.m. US Central Time. All right, so I'm going to share my screen. All right. Can you all see the first question? So this one involves a tangential quadrilateral, which we don't do that. I haven't done that many problems with, I feel like. So here's how I think I'm going to do it. So I'm going to draw the in circle of this, and then I'm just going to kind of cheat here. There we go. And then I will just pick a random point here and draw the tangent from D to the circle. But I'm going to have to rename stuff. So this should now be C. And this should be D. And then I will hide a whole bunch of stuff. I don't know if that's the fastest way, but I've done it like that before. So, all right. And so O is the center of the circle. And I is the in-center of ABD. First, I'm going to draw the in. Well, I want I to be the in-center, so not the in-circle. So let's see what happens if I do this. Oh, it doesn't like that. Okay. So I'm going to change this to, I'll call it B. So I is the center of B. There's O and I. So then we have a line passing through O and perpendicular to BB. So let's make, let's do something like that. And it intersects that circle at F, and F is in the interior of ABD. And we want to show that, okay, and E is the intersection of AC and BB. Wait, did I do something wrong here? I think I might have done something wrong. So that looks tangent, but it,
you took a in center of ABC.
Oh, that's the problem. Okay. All right. Let's see. There we go. And so this should be point E. There we go. That looks much better. So here's E, and we want to show I, E, and F are collinear. I want to keep this perpendicular line. So let's see if I can draw this point. It's hard to make the points far apart. There we go. Okay. So let's hide this. Just draw the segment FG. Okay, and I'm going to close this. Maybe it might be better to kind of do it like this. Basically make A at the top because we want the line passing through O perpendicular to BD. So if I move C around, it's a tricky diagram. It almost looks like these are parallel, but let's see. If I move things around a little bit. Maybe that's fine, like that. They almost look parallel. We'll just have to remember they're not parallel. Okay. Yeah, let me see. Can I rotate this figure a little bit so it's a little nicer? Yeah, maybe something like that, and then make it a little bigger.
I'm pretty sure we should add the in circle of BCD.
The in circle
diagram.
BCD. Okay.
Yeah.
So AI and O are collinear.
And the interesting thing is that those two in circles are tangent to each other.
Okay. So is that like a well-known fact that they're tangent?
To me, yes.
It's just a length. It's probably just a length chase, right? Because
probably, yeah.
Yeah, because basically this segment is just BD plus BC minus CD over 2. And we want to show that's the same as BD plus AB minus AD over 2. And then that's just length chasing because, yeah. Okay. So then we can draw the segment IH, and that's perpendicular to BD, right?
You could also extend OG to other intersection point of the incircle of the quadrilateral.
Okay. Let's see.
So by symmetry, we would also have a pair of collinear points. Should have.
So J, H, and let's see. J, H, and E are also collinear, but would be collinear by symmetry once we can prove one of them. Okay. Yeah, let me make this look a little, it almost looks like AE is perpendicular to BD. When it's not perpendicular though, the diagram looks like it's hard to make a good diagram where it doesn't look that perpendicular. So yeah, we'll just have to remember it's not perpendicular. All right. Oh, congrats, Akan, on your on the silver medal at the IMO. That was awesome. All right. So yeah. All right. Yeah, and I think you weren't that far away from a gold either, if I remember. So yeah, that's pretty awesome. Okay, so how could we show that these are collinear? So, I mean, basically we want to label this point here, and we want to use like ratios might work. So because these two are parallel, we want to show that FG over GK or FG over IK is GE over KE, right? Oh, I didn't check the exact numbers, but interesting. All right. Yeah, still pretty awesome regardless.
I think we should try to prove that OE bisects EH.
OE
IH.
OE bisects IH. Interesting. How did you find that?
It follows if the problem were true.
Okay.
But it isn't quite enough to prove the problem. It is not equivalent, but it is useful to prove.
It would follow. So we know C, H, and O are collinear. Probably draw that. Yeah, let me I'll do this. Here we go. Now these really look all parallel. Okay. So IK is just the radius of the circle. FG, can we say anything about that? Yeah, what's the best strategy here? Hmm. Hold on 1 second, I have to do this. Sorry. All right, sorry about that. So let's see. Um, okay, so yeah, is there some kind of homophily, I wonder, that could solve this? So let's see, if the problem were true, we'd have basically we'd have FG over, can we show that FG over GJ is IK over KH? Because IK and KH are the radii of the two circles. Yeah, maybe we can do it like this. So first we want to show FG over GK is IK over KH. And then if that's true, then maybe we could show like FI. We could try to show that FI, GK, and JH concur. Yeah, I don't know if that would be strategy. Yeah, I just don't know how to get the distance FG. But yeah, this problem looks kind of familiar. Like I feel like we've done it in some previous session, but like I think Khan or one of the people from Vietnam had a solution to this. So I don't know if this will help at all, but it's like L, O, and M we know are collinear by what is it, Newton's theorem, where L is the midpoint of BD and M is the midpoint of AC. Yeah, I think that might just make things more confusing, so I'm going to erase that. I feel like there's some theorem like EO and because there's something called like maltitudes, right? So it's like, I think there's some theorem. Isn't there some special point in a tangential quadrilateral called like the maltitude? Oh yeah, now I think I remember what it is. You take the midpoint of each side and then you take the altitude to the opposite side. So for example, if I take this altitude and I take this altitude, and then if I think if you do it for all four of the sides, it concurs. But I thought it concurred at a point on OE, but it doesn't look like it from this picture. First, let me see if that theorem that I'm saying is true. So, yeah, I don't think it's even true what I'm saying. I thought that all four of these like concurred. But I must be thinking of something else.
Oh, okay. I think I have found something that may be useful.
Okay.
So a tactic how we could possibly prove that OE bisects IH.
Okay.
So take a parallel to IH through O.
Okay. So that's just this line, right?
Oh, yes, actually, I didn't notice that. Okay, then it is even better. And intersect that line with AC.
Okay. Oh, that intersection is going to be far away. Okay.
It will be here.
Let's see. Yeah, let me see if I can draw this a little differently. Yeah, what if I, let's see, I'm going to figure this out. So let me, if I make this more of a taller triangle, that looks better. Okay. But yeah, then O and G, Oh, wait. This is O. Yeah, that's not so bad. Okay. So I'll let those intersect at that point up there. Okay.
Okay, now label the tangent points of the in circle of the quadrilateral.
Okay.
For example, those two, and Mn should pass through L.
Okay. Is that by like the radical axis theorem or something, or projective geometry?
I don't know why it is true yet.
Okay. So L lies on the polar of B. So B has to lie on the polar of L. I wonder if BD is the polar of L. Is that? Oh, Pascal's theorem? You might be right.
Well, I know how AC and like Mn and the other line with the tangent points concur, but not exactly sure if it is obvious also for line LO.
Okay. Okay, so Hakan is saying that this should follow from Pascal's theorem. So yeah, it feels like this must be like some well-known configuration. So we let Mn and PQ intersect at a point, then we need to show LO is perpendicular to BB. So L lies on the polars of both B and B. So BD has to be the polar of L. And so that proves that OL is perpendicular to BD. And then we just have to show it lies on AC. And yeah. So yeah. So OF we can show is perpendicular to, well, it's defined to be perpendicular to BD, but yeah, I can show that MN, PQ, and OF concur, but then we have to see if it passes through AC, and maybe the
Yeah, I know how to prove that it passes through AC. That part is not hard. I think it is some polars.
Okay.
Or something. So now, can we prove that ACEL is harmonic?
Let's see.
That looks like something that shouldn't be very hard to prove.
Yeah, I wonder if we can use polars for that. Because we know LFGJ is harmonic, right? Because G's on the polar. We want to show LAEC is harmonic. That's what you're saying. Well, actually, yeah, it's kind of obvious because basically, if you project through B onto MN, LAEC goes to LMRN, and since R is on the polar of L, then those have to be harmonic. So that proves it.
Okay, then we know that OE bisects IH by a projection through O.
Okay. That makes sense. All right, so OE bisects IH. And how did you see that that follows from the if the problem were true?
Oh, that is actually a thing I have done many times on some sessions here. So we have that FJHI is a trapezoid.
Okay. Yeah, it's a trapezoid, yeah.
And O is the midpoint of FJ.
Okay.
And S, well, let's define it as the midpoint of IH.
Mm-hmm.
Then by Child's theorem or something, Fi, Os, and JH should concur.
That makes sense, yeah. Like a homothety. E is the center of, yeah, that homothety.
Yeah.
Interesting. So I think we know that Fi, JH, and OS concur. We just don't know that they concur on BB, right? Yeah, because they're parallel. So like maybe we could hide BB and then like we know that these three concur and we have to show that the point that they concur at is on BD. That could be another way to do it. So if we can show E, K, and G are collinear, that would solve it. But yeah, how would you define G and K? That's the thing. I think we're close here. So if we know OS and E are collinear, then we know that GK over KE, that's OS over SE. And we want to show that's like FI over FE or FG over IK. Hmm. let's see. If I, E, and F were collinear, we could project them like, yeah, if they were collinear, then we could project through O onto LC. So F goes to L, I goes to A, E stays at E. I wonder. I wonder where OC and if OC and EF intersect at some point. It's like Ravi is joining. Hey, Ravi, thanks for joining. So Hakan mentioned your contest, so I might participate in it. I'll take a look and see if I have time. But thanks for sharing it. So, oh, sorry, Stefan said it. So we made a decent amount of progress on this problem. So yeah, it has a pretty simple statement, I feel like.
Could we compute EG, EK or EG?
So EK over EG, that's the same as ES over EO, right? I don't know if that helps.
Yeah, but now because we know these midpoints are linear and stuff, we need to show that EK over EG, that is equal to IH over FJ.
Yes.
And those two are okay lengths. We can handle them, I think.
But like IH is the sum of these two radii, and
Yeah.
FJ is so yeah, we knew FJ and IH were parallel because they're both perpendicular to BD. So we kind of knew that from the beginning, even before we knew about the midpoints.
Oh.
But yeah, but it still looks like it might be a good idea. But yeah, how do we find, so FJ, let's see.
FJ is twice the radius.
Oh, that's right. I don't know why I keep forgetting that. FJ is twice the radius of this, and IK and KH are each the radius. Okay, so yeah, I see what you're saying. So yeah, let's see. Is there a way to do GK over KE? Maybe we can project through O. Let's see. Or project through L. Actually, yeah, let me try this. So if we do GKE infinity, like try to project through O. Yeah, it's just not clear where K would go. Oops. Hmm. Yeah, I'm still thinking about like, what if we let Fi, JH, and OS concur at a point, and then we want to show that point lies on BD. Let me try reflecting E over O. So if we reflect E over O, I thought there was something special about that point, but I might not be correct. Oh, you know what? Let me if I draw these four midpoints, we'll just draw and then I take the perpendiculars. Yeah, that's not what I thought. Yeah, I forgot what the property was. So I'll be right back. All right. All right, let's try this problem for like 10 more minutes, and then we could maybe go back to it later. I think we're close. Like maybe we could find the cross ratio GKER.
Oh, I think I may have solved it, but it looks a bit strange.
Okay.
Okay, so intersect the JI and FH.
Okay. JI and FH.
That lies on OS.
Okay. That's true by Cheva.
Yeah.
Or just similar triangles, yeah. It doesn't want to draw the point instead.
Yes.
There we go.
Now we want to show that SOTE is harmonic.
Okay.
And we project through G onto IH.
Okay. Okay, O, T, S, and E. So O goes to infinity, and then we have H, S, K, right? So that would be.
It is KS and the intersection of GT and IH.
GT, oh, sorry, GT and IH, right? Okay.
GTIH.
All right.
So basically, if we want to prove that the cross ratio OSTE is harmonic, then we want to show that S is midpoint of KU.
Okay.
But so like this, G and U, they are corresponding points in triangles, similar triangles TFJ
Okay.
and TIH.
Okay. So we have TFJ and TIH, and G and U correspond to each other.
And we get that FG or GJ.
FG over GJ
is UH over UI.
Okay.
But we also know that FJ or FG or GJ is IK over KH.
Yes.
And does that prove that S is midpoint of KU?
Okay. So IK over KH is equal to HU. Yes, it does. It does. FG over GJ is IK over KH. Oh yeah, how do we know that?
Oh, that was the mistake. Yeah, it looked like strange.
Okay. All right. Let's see. Interesting idea. So we want point S. So is there something we can project through? So What if I project Fi and E through A onto OC? So if those were collinear, we could do that projection. Yeah, it feels like we should be able to, we want to show FG over GJ as IK over KH. But FG and GJ, that's basically where you take the perpendicular from L to BB and you see how it splits these two. So is there a way, like maybe we could show, that seems like it might not be so bad to show. Because BB is the polar of L, right? And so L, F, G, and J are in harmonic conjugation. I think that might help us a little bit. Because since those, because L, F, G, and J are in harmonic conjugation. So FG over GJ should be LG over LJ. Isn't that right? Or LF over LJ. I think that's right. So we want to show LF over LJ is IK over KH. And I don't know if there's some way to do that with similar triangles. Because we know LF times LJ, that's going to be the power of L. Can we get some similar triangles? I wonder what happens if we take the tangent from L to the circle. So do these, so these concur. Basically, if this point is T, LT is going to be tangent. And the same on the other side too. I'm just going to draw this one for now. And then, whoops, because we know BD is the polar. And then we want L, so LFT is similar to LTJ, right? And so from there, can we get rate any, well, I forget, isn't there some theorem about like LF over LJ is like, isn't it like FT over TJ squared or something? I don't know how helpful that is, but I think, yeah, oh yeah, FT over FT squared over TJ squared. So basically we want to show FT squared over TJ squared is IKH. And we know that FJ is a diameter, right? So, well, okay, now we actually just want in a circle, right? Because FTJ is a right triangle and TG is the altitude. So FT squared over TJ squared is going to be FG over GJ. So we just want in a circle. Yeah. Whoops. So wait, G is going to be the midpoint. Like if we draw these 2 points, so it's hard to draw the one right here, but G is going to be the midpoint of that by symmetry. Yeah, like I think it's worth drawing this point and this point. All right. You guys want to try a few easy problems and then come back to this, or do you want to keep sticking with this? I think I might come back to this later. I think we're close, but I want to solve a couple problems. So let's see. It's a good one. This one looks like it's not so bad, right? All right. So we have a triangle ABC inscribed in a circle O. And P is a point on BC. O, P is any point, and then we project onto AC and BC. So that's going to be X and Y. And obviously we have a cyclic quad there. And then M is the midpoint of AP, so M is going to be the center of that cyclic quad. In fact, before I even, so I'm going to draw it, and then this center of it is M. And then I can draw the altitude AH. Just going to lie on that. Okay. And then we have a point, then we draw the circumcircle of mxy. So mx is equal to my. So that might be helpful. MT is parallel to BC. Okay. And then we want to show that TO and P are collinear. So let's see, MT is going to be the angle bisector of XTY. All right. So this is parallel to BC. It also bisects angle XTY. I don't know if that's helpful. It might be, because we might be able to get like a harmonic bundle, like if we drop a perpendicular from T to BC. All right. We want to show TO and P are collinear. I don't want to make it look like O lies on the circle. So something like that. But this almost makes it look like, yeah, I'll do something like that. So can we use that harmonic bundle or not really? We could try projecting onto BC. So basically, well, yeah, TX and TY, if we intersect it with BC, we get like an isosceles triangle, although I'm not sure how helpful it is. Well, wait, that might be useful. I wonder if, no, that's not true. Well, wait, so angle YMX is twice angle A. Oh, so YMX is similar to BOC. That's probably helpful, right? Yeah. That's got to be helpful. So basically, I wonder what T corresponds to. we could see, yeah, what does A correspond to and what is, So let's do this. Let AP meet the circle at a point. And then so we could draw OD. So basically AYPX, if we draw this point, it's going to be similar. AYPX is similar to EBBC. Okay. And T, yeah, what do we do with T? So MT is perpendicular to AH. So hold on a sec. I think this might, let's drop perpendiculars. So maybe we could show OF over PF is TG over PG, because OF is half the distance from A to the orthocenter. And TG is half of AH, right? So that could help. Yeah, TG is half of AH and OF is half the distance from A to the orthocenter. So really we could just draw the orthocenter of ABC, call it K. And we just want to show that AK over AH is PF over PG. And maybe that's not as easy as maybe that's not so easy, but that's just another way to rephrase the problem. So PF over PG, can we calculate that? And maybe it's worth drawing the center of this big circle. So it's I. So PF over FG. Is there any way we can think about that in a different way? Can we project PF over PG? So I wonder what T corresponds, because BOC is similar to YMX, but what would T correspond to there? Be some point like right here. So yeah, what if we did that? We try to see BOC, because BOC would, that circle would correspond to the circumcircle of MXY. And here we're taking the parallel to BC. Yeah, I'm not sure. Would it be this point? I don't know. I think we need to find something special about point G. Okay, so maybe triangle AHF is similar to PTG. Let's see if that's true. Whoops. So angle HAF is 27, and angle GPT, no. Maybe if we, wait, so, oh, are you doing moving points? Let's see if we can yeah, so sorry. Let's try a couple more minutes solving it without moving points, and then we could do that solution if we can't figure it out. So that's 24. All right. So yeah, but maybe the idea of moving points would help, because like if P is the midpoint, if P is the midpoint, that doesn't do much. But basically we're saying PF over FG is a constant ratio. So my GeoGebra froze, I think. We're saying the ratio PF over FG is constant as P moves. So is that obvious? So if the ratio PF over FG is constant, what does that mean? All right. We move T on the midline of ABC. Okay. Let's see. So so from T to P, so we have TO intersect BC. All right. So let's see, yeah, if we can prove it for specific choices of P. If P is the midpoint, then yeah, so we could try if P is, I guess we could say if T is B, P is H, and P is the midpoint or something like that. Midpoint is probably easy. So if P is the midpoint, let's see, then we want to show T. Yeah, P is the midpoint. Is it trivial? Basically, we want to show, so you're taking the midpoint of the median and you're taking a parallel to MTX or MYX. Okay, so yeah, how do we do the midpoint? I'm just thinking about this. Um, So yeah, PF over FG. Let's see. So we have someone else joining us. Hi, Nguyen. Thanks for joining us. So we're on our second problem. And yeah, we made a little bit of progress. We were thinking about using moving points. So yeah. Basically, we start with any point P on BC, and then we draw perpendiculars X and Y. And M is the center of this circle. And then we draw the parallel from M to the circumcircle of MXY. And it intersects the circle at T. And then we want to show TO and P are collinear. So that's the problem. All right. So yeah, FG. Wonder if there's a way to think about this. So MT is parallel to BC. So by symmetry, So FG is FC minus CGC. Is there anything special about this? So we know that, okay, so M is the midpoint of AP, O is the midpoint of ED. Yeah, so moving points is not that hard of an idea to prove. So yeah, I wonder if P is equal to B, let's see if it's obvious. If P equals B, then we're okay. Then we take the circumcircle. This, I think it's trivial if P equals B, because then basically we want to show that angle MTO is equal to angle ODC. And I think that should be obvious. Yes. Because angle MTD is angle MKD. And they're similar. So it's obvious that P is equal to B and C. And then, is it obvious for a different point? Let's say P equals H. So basically, we're just taking the midpoint of the altitude. We can compute PF and PG if P equals H. So what's PG? Okay. So if P is equal to the midpoint, I don't know if that's obvious. If P is equal to the midpoint, is XY parallel to BC? I don't think so. No. But we could try to show that angle MTY plus YTP is 90. I think it's better if P equals H. Because then the circle's tangent to BC. If P equals H, does T lie on the circumcircle of ABC? I think that's a coincidence. Because like, if I change triangle ABC a little bit. Yeah. So if P equals H, they're tangent here. And we want to find P F over PG. Sec, I'll be right back. All right. The third choice of P, I was thinking about that. So P would be the point at infinity on line BC. So if we make point P like, P is the point at infinity, then M is basically M would be the midpoint of this. So that would be M. And then what would be the perpendiculars from P to AC and AB? Trying to think. Yeah, how would that work? Y and X would also be on AB infinity and AC infinity. Okay. And what would that, yeah, what would that look like? So you'd have the perpendicular, you'd have the parallel, this parallel line. So would it just be, what would the circumcircle of MXY look like? Would it just, so P, so yeah, so when T is so P would be BC infinity. Okay. Oh, because it's a way to find the functions. Okay, because T is moving on the midline. You kind of redefined it. Okay. Let me, okay, I'll copy your proof into here. All right. So we use the method of moving points. And then here's the second one. Oops. Let me get rid of the LaTeX just for now. All right. So if P equals B, the problem is obvious. See how this looks. Okay, so we have TO intersect BC. And then you take y on AB such that the angle it makes with the midline of TY So when you say midline, do you mean the angle that PY makes with AY? Turn it here from Y to AB. And let it cut BC at P. Okay, so this you draw the midline of TY equals 90 minus A. Just trying to understand that. Do you just mean the angle TY? Oh, the angle TY makes with the midline of, okay, the midline of ABC. Draw like that. Okay. It's angle MTY. Okay. So from T to Y, it's projective, and Y to P is projective. Okay. And then, so it's, first I'll say it's easy to see that the problem is true if P equals B or P equals C. I'll say, I'll just write this out quick. Since triangles X, MY, and BOC are similar, the problem is easy to show by an angle chase if P equals B or P equals C. And then if P is the point at infinity, then, or if T is the point at, well, if P equals B or P equals C, so yeah, these correspond to two different choices of T. I'll say that. T. And then next we look at if P is the point at infinity. Okay, so when P is the point at infinity on BC, then T is also, it's like the point at infinity on MT, and then the problem's kind of true. Okay. Because this circle just kind of gets wider and wider, right? So yeah, unfortunately I can't move it past point P in the way I drew this, but so T is at infinity, P is at infinity, and then is it clear that if that's true, I guess it's obvious, right? Let's see. Basically, we're saying, okay, be the point of infinity. Yeah, I'm just getting a little confused here. But basically, you're saying it's easy to see in that last case, right? That's what you're saying. Okay, I'm just going to write that out. Okay, I'll think about that later. I just want to solve some more problems now. I didn't LaTeX anything else, so I won't do this. Points T, O, and P are collinear. All right, I'm going to move on to another problem. Thanks for the solution. But yeah, there has to be a synthetic solution to this. I might look for it later, but yeah, this is good enough for now. All right. Okay, let's try this one. So we have the in-center of ABC.